So here we're going to go through homework 2 on gravitational fields. Question 1. State the law that governs the magnitude of the force between 2 point masses. So this is basically just a question asking us to state Newton's law of gravitation. So we know what Newton's law of gravitation is, or we should do. The force between 2 point masses, or between 2 spherical masses, is proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so 1 mark for proportional to the product of masses, second mark for writing down that the force is inversely proportional to the square of the separation. We've got a table here then showing how gravitational potential varies for 3 points above the centre of the Sun. Show that the data suggests that the potential is inversely proportional to the distance from the centre of the Sun. So we know, of course, that gravitational potential is given by minus g over r, and therefore Newton's law, Newton's gravitational constant here, universal gravitational constant, is constant. The mass of the Sun, of course, is not going to change, so the top of this is a constant, and so what we have here is gravitational potential is inversely proportional to the distance from the centre of the Sun, or if you like, V equals some constant over r, and what that means then is that VR should equal a constant. Okay, so if the gravitational potential is inversely proportional to the distance from the centre of the Sun, well then VR should equal a constant. So all we've got to do really here is multiply the gravitational potential by the distance from the centre of the Sun and check that we get the same value each time. So what we can say here then is 7 times 10 to the 8. If we multiply that by 19 times 10 to the 10, we get 1.33 times 10 to the 20. If we do that for the 2 other rows, so we can see that for each row, V times R is giving a constant value. In other words, V over R, or V equals a constant over R. So they are inversely proportional. VR equals a constant. So there we go, just work out VR for each row in the table, giving us the same value, giving us a constant, and so V and R must be inversely proportional. Use the data to determine the gravitational field strength near the surface of the Sun. So use the data, so it really wants us to use the data that we've got here. Part 2 follows on really then from part 1. We've worked out this constant here. What is that constant going to be equal to? Well, look here, gravitational potential equals minus gm over r. So V times r is a constant. What is that constant given by? Well, it's given by gm. So we've really worked out here the mass of the Sun multiplied by big G, the gravitational constant. So if we know gm, we also know that gravitational field strength is given by gm over r squared. We know that gm here is equal to, because we've worked it out here using this first part, working out this constant, and so we can say, look here, G, gravitational field strength, small g, is going to equal 1.33 times 10 to the power 20 divided by, well, we want near the surface of the Sun, so the surface of the Sun is 7 times 10 to the 8 meters away from the centre. So we want to put r in as 7 times 10 to the 8 meters. Don't forget that that's got to be squared, and then we just need our calculator and work that out. There we are, 271 newtons per kilogram. That question then straightforward, provided you've realised here that you can use the formula for gravitational potential. If you're given the gravitational potential and you're given the distance from the centre of the Sun, you can work out using the gravitational potential formula, gm. And then if you've got GM and you've got the distance from the centre of the Sun to the surface, you can work out the gravitational field strength at the surface of the Sun. Calculate the change in gravitational potential energy needed for the Earth to escape from the gravitational attraction of the Sun. Okay, well, we've got the mass of the Earth, we've got the distance of the Earth from the centre of the Sun. Now, what we know is that an infinite distance away from the Sun, the gravitational potential will be 0 joules per kilogram. What about at a distance from the centre of the Sun equal to the Sun-Earth distance? Okay, so at the position of the Earth, V will equal minus GM over R, of course, which will equal, well, again, we just worked out GM, 1.33 times 10 to the 20. That's the mass of the Sun multiplied by big G, GM, 1.33 times 10 to the 20. We can divide that then here by the Sun-Earth distance, which is 1.5 times 10 to the 11. And we've worked out 8.87 times 10 to the 8 joules per kilogram. So any mass placed in a position equal to Earth's orbital distance from the Sun is going to experience a gravitational potential of 8.87 times 10 to the 8 joules per kilogram. An infinite distance from the Sun, of course, V equals 0. So if we were to move the Earth from its position it is now, and the Earth was to escape completely from the Sun's gravitational field, it would be moving from a gravitational potential of 8.87 times 10 to the 8 joules per kilogram to a gravitational potential of 0 joules per kilogram. So the change in gravitational potential energy of each kilogram of mass is just the difference between those two. Yeah, I would have to put in, it should be a minus there, I've got to put in 8.87 times 10 to the 8 joules of energy for each kilogram of mass to go from that potential to 0. So the work done, the total work done, the change in gravitational potential energy is just m delta V, because of course the mass of the Earth isn't 1 kilogram, it's actually 6 times 10 to the 24 kilograms. So if we multiply the mass of the Earth in kilograms by the amount of energy needed to move each kilogram from the Earth's orbit to infinite distance away, which we know is the difference between these two values, what we will get is 5.3 times 10 to the 33 joules. That is the energy required to move the Earth from its orbit now to an infinite distance away from the Sun. That would be the amount of potential energy it would gain going between those two positions. Calculate the kinetic energy of the Earth due to its orbital speed around the Sun, and hence find the minimum energy that would be needed for the Earth to escape from its orbit. Okay, so we've got the change in gravitational potential energy. Of course, the Earth has some kinetic energy in its orbit. Could we work out its kinetic energy? Well, kinetic energy, of course, is half mv squared. We know the mass of the Earth. Do we know the orbital speed of the Earth? Well, we do know that the Earth takes 365 days to orbit the Sun. So the speed of the Earth would be distance divided by time, and so that would equal 2 pi r divided by its orbital period. The radius of its orbit, well, that's just the distance from the Earth to the center of the Sun. So that's 1.5 times 10 to the 11 meters. And of course, the period of its orbit, 365 days. Well, we need to convert that into seconds. There's 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So we can work out then the speed of the Earth. And there we are. I've written that down to 5 significant figures just to avoid a rounding error at the end. So calculate the kinetic energy now. Well, that will be a half multiplied by the mass of the Earth we were given earlier, We need to multiply that then by our speed. Alright, let's go back to our question. Calculate the kinetic energy of the Earth due to its orbital speed. Well, we've done that. Hence, find the minimum energy that would be needed for the Earth to escape from its orbit. So we know that to escape from its orbit, it's gaining 5.3 times 10 to the 33 joules of potential energy. It already had 2.68 times 10 to the 33 joules of energy. So how much additional energy would it need to be given on top of that in order for it to move an infinite distance away from the sun and to have zero kinetic energy at that point? Well, it's just the difference between those two values then. So we can do 5.3 times 10 to the 33, take off the kinetic energy of the Earth, 2.7 times 10 to the 33. What are we going to get? Well, we're going to get 2.6 times 10 to the 33 joules. So at the moment it's got 2.7 times 10 to the 33 joules of kinetic energy. If all of that, together with another 2.6 times 10 to the 33 joules of energy that it was given, if all of that was converted to gravitational potential energy, the Earth would be able to move an infinite distance away from the sun. In other words, it would be able to escape the gravitational attraction of the sun. What about question 2 then? For an object such as a space rocket to escape from the gravitational attraction of the Earth, it must be given an amount of energy equal to the gravitational potential energy that it has on the Earth's surface. The minimum initial vertical velocity at the surface of the Earth that it requires to achieve this is known as its escape velocity. Write down the equation for the gravitational potential energy of a rocket when it is on the Earth's surface. Okay, so we know that gravitational potential will be given by minus g, the mass of the object that's providing the gravitational field, which is the Earth, and we're told that that's got a mass big M, and the radius of the Earth, we're told to take that as r. So the gravitational potential, that's the gravitational potential is the energy of a 1 kilogram mass. So if that's the gravitational energy of a 1 kilogram mass, if we multiply that by the mass of the rocket, then we'll get the gravitational potential energy of the rocket. So what we're going to get is minus g big M little m over r. Yes, so if gravitational potential, remember, is in joules per kilogram. So if I multiply the number of joules per kilogram that the rocket has by its mass in kilograms, I'll get the number of joules that it has. So that, quite simply, is all we need there. Show that the escape velocity is given by that equation. Right, okay, well that's going to be straightforward. If that's the amount of gravitational potential energy that it's got at the Earth's surface, it's going to have zero gravitational potential energy when it's an infinite distance away from the Earth's surface. So how much energy have I got to put in to get it from minus gmm over r to 0? Well, I've got to put in an energy equal to gmm over r. So really it's just the fact that the Ke lost here by the rocket in escaping from the Earth's gravitational field will be equal to the GPE that it's gained. Kinetic energy we know is a half mv squared. M is the mass of the rocket. We've just said here the gravitational potential energy it's going to need to gain to get from that value to 0 will be gmm over r. So what we can do is cancel the mass of the rocket, multiply both sides by 2, and then square root. So v then is going to obviously equal the nominal escape velocity from the Earth is 11.2 kilometers per second. Calculate a value for the escape velocity from a planet of mass 4 times that of the Earth and radius twice that of the Earth. Okay, so if we were using this formula here with the mass of the Earth and the radius of the Earth, we'd get 11.2 kilometers per second. If we had another planet which was 4 times the mass and twice the radius, okay, well 4 times m, half the radius of what we're going to have here on the right hand side, compared to what we had before, the mass is 4 times bigger, The radius is twice as big, everything else is the same. 4 over 2 is 2, so we get the square root of 2. So compared to what we had before, what we've got now is the square root of 2 times bigger. And so our escape velocity is going to be the square root of 2 times bigger. So all we need to do is 11.2 times the square root of 2, and we will get our new escape velocity, 15.6 kilometers per second. Explain why the actual escape velocity from the Earth would be greater than the nominal amount calculated from the equation given in part A. Part 2. Here we're saying that it's 11.2 kilometers per second calculated using this formula. Well, of course, in that formula, all we're assuming is that kinetic energy is just converted to gravitational potential energy. Of course, one thing we have neglected to consider is that the Earth does have an atmosphere. And if you're going to move something through the atmosphere at very, very high speeds, it's going to encounter very, very considerable air resistance, which is going to convert energy into thermal energy. So the answer is, whilst it's moving through the Earth's atmosphere, a lot of the kinetic energy of the rocket is going to be converted into thermal energy rather than kinetic energy. So we're going to get a lot of energy lost in that way. So we're going to have a much bigger kinetic energy to begin with to account for the energy that we're going to lose to thermal energy. So provided you realised that the Earth had an atmosphere, that last part fairly straightforward. And there we are, homework 2.